Nice. Yeah, welcome to my talk. Thank you all for coming. My name is Heike Hallenberger. I work for DB Systel in Germany as a software developer. And I want to tell you a little bit on how we use Chef to manage a data center on Rails. So, and it's actually about this kind of trains we see here. First, a little bit about the company I work for. So again, my name is Heike. I work as a software developer for more than 8 years. It's more around 10 years, actually. And I work for a company called DB Systel. We're located in Germany. Our headquarters is in Frankfurt. We have office sites in Berlin and Erfurt, as well as office site in the UK. There are around 4,000 people working at DB Systel. And we are the IT integrator and enabler for the DB. We are a DB subsidiary, and we have great knowledge, of course, in the IT industry and in the rail sector especially. The DB is a large German railway company. It has around 300,000 employees, and it's one of the biggest employers in Germany. And there are 19 subsidiaries in the DB. A little bit about the project I work in. So we are called FlexFit. FlexFit means Flexible Vehicle IT. And we're around 6 to 9 people. Our customer is DB Fernverkehr. And Fernverkehr means long-distance intercity travel. So the DB Fernverkehr operates the high-speed trains we saw on the title slide. They operate 255 of these high-speed trains in Germany. And the DB Fernverkehr had a vision. They wanted to build a platform in the trains that provides information and entertainment for the customers that are traveling on the train. And this is the hardware platform I'm talking about. So one of these platforms is built in each of the 255 train sets. And the platform has a lot of different connectors like USB, RS422, RS232. It has a small display and status LED, and it has a lot of storage. And it is connected to the internet gateway of the train. The high-level architecture of the platform was supposed to look like that. We have 2 server sites actually on this platform. They're independently working. We have a left side and the right side. The right side is for the consumer services on the train, and the left side is for the operational services on the train. And it was planned to keep the base system as slim as possible, so any additional services we would provide in virtual machines running on the platform. Also, we would have enough space for third-party manufacturers to provide their own virtual machines with additional services. So what were the main requirements, and maybe also a bit the special requirements in an environment like that? So, of course, first of all, we have 255 train sets. That would mean 1 platform per train set, and so we're talking about a large number of servers already we had to maintain, and we don't want to do that by hand, so we were looking for a system management tool that could support us doing that. One main requirement was what our customer wanted is that we actually could provide new software in a short amount of time, and we could also apply security patches in a short amount of time. This requirement is maybe given for any normal environment, because of course you want changes fast, but in an environment on a running train, it's a bit more hard to accomplish. I will tell you a little bit about why it's so hard. So first of all, you have a train that is traveling around the country, so you cannot really just get it whenever you want. Another part is as soon as you build a platform for a train and it is connected to the train, you have to make sure that it is non-intrusive. That means that your own system you implement does not send any signals to the train. Because as soon as you have that situation, the federal railway authorities in Germany, of course, and they want to make sure you don't influence the train in any bad way. So that means you have a lot of rules and regulations how you have to develop the software that is running on the train. And that means, again, that there is a long process because you have to give the software to an auditor that checks the software and has to approve of the changes you actually make. And this is the opposite of being fast, of course. So in our project, we made it a bit different because we like change too. We gave the responsibility for the non-intrusiveness to a gateway. So actually, we are not directly connected to the train control system, like here, because then we would have these rules and regulations with the software. But we are connected to a gateway. And that gateway guarantees the non-intrusiveness. So actually, we are able to receive data from the train, but we cannot send any data to the train. And that gives us the freedom to operate faster and to use more flexible software in that case. Another big point is how do you actually deploy software to a moving target? So is it just as easy as connecting it to the internet and receiving this new software you want to deploy? It's not that easy, but I will tell you a bit more about the classic way, how it was done until now. So usually you have the trains, and there are a couple of big maintenance depots around Germany, where they go from time to time. So usually if you want to deploy new software on the train has to go to that maintenance depot. Someone has to go on the train with a hard drive and change it on the platform. So this is how you get new software, because the internet is of course also not that stable, so that you can transfer the big data. But this is of course also not fast, and it takes a lot of planning. So it takes some weeks in advance to plan when will the train go to which maintenance depot and what software does it get. So our customer of course had the requirement to reduce the amount of times we would have to go to the maintenance depot. Not only that, it's also very important, of course, what is the worst thing that can happen to our platform? That would be that we lose the connection somehow, so that the platform would ride in the train and no one could access it. So we have to make extra sure we don't break the platform with any software change we make. So we cannot completely remove the updates in the maintenance depot, but we can reduce it. So if we have any big changes, for example, we reconfigure the network on a whole new level or something where we could break the platform, we still do hard drive releases, because it's just not secure enough to release that over the air. Another requirement we had was that, especially when we're in the maintenance depots and new major versions get updated on the train, we don't always have internet connection. So we had to make sure whatever we deploy, it could also be deployed in an offline environment. That brings me to the next point. Why did we use Chef? So our servers can only pull. It means our platforms don't have routable internet addresses. And the Chef and the Chef server, of course, support that mechanism. Our back office is set up in the AWS cloud. So we already had some experience with OpsWorks and Chef and found that to be stable, so we could use that knowledge. Of course, the great community with all the cookbooks we have, so we did not have to invent everything by ourselves, because you know it, there are a lot of cookbooks you can just reuse and apply to your own notes. And Chef supports the local mode, and that was exactly what we needed for the offline requirement. That means we can use the same cookbooks offline that we use online. So in the end, our architecture looked like that. We have the hardware on both sides of the platform, of course. On top of that, we run Scientific Linux that is fully managed with Chef. And on top of that, we use KVM virtualization. We run virtual machines. These two in blue are provided by our project, and they are also fully managed with Chef. So we have 4 Chef clients per platform. These guest virtual machines are not provided by us, but from other manufacturers, and we don't know actually how they do their system management. It's a black box for us. And our platform communicates to our back office that's set up in the Amazon cloud, and we run our own Chef server there and some other servers next to it, like an operation center and SSH server. SSH, maybe because I said before they don't have routable IP addresses. That's true, because only the trains know when they are online, so they connect to the server. So we cannot just connect to the servers if they are not online, of course. So they open the tunnel from the trains to the back end. The important points were, as I said before, offline and self-containment. So how does it actually work? When we have a major release, we have the hard drive change, and someone actually in the maintenance depot has to go to the platform and change it. We then update the platform with the image that is on the release. And then we have a Chef local mode. So we have two different Chef runs. We have an online version and an offline version. And that offline version here makes sure the platform is in a status where we can operate it online as soon as it has internet connection. The most important thing from the offline mode is that each platform has a unique identifier, and Chef reads that and saves it. So as soon as it's online, we have a mechanism that identifies and activates the platform in the back office, and then the back office actually creates a node in the Chef server. And as soon as that is done, we are in the Chef online mode, and the trains receive the latest updates. And one of the most important things I mentioned before is, of course, our platforms. We cannot afford for our platforms to be lost, so we have to make sure they stay connected to the Chef server. And for that, we build mechanisms, of course, that monitor if the Chef client is still connected to the Chef server. And as soon as that's not the case anymore, the identify and activate mechanism gets re-triggered. So after that, hopefully we have again a running Chef on the platform. This mechanism is set up for all the four Chef clients we have on the platform. So what do we actually develop besides cookbooks and recipes? We provide a lot of different services on the platform, for example, a train data service. We use a lot of different technologies like Python, Java. We build a lot of systemd services. And in the back office, we have a lot of different cloud computing technologies. We verify everything locally with Chef specs. We run Test Kitchen. Of course, we have a build server that runs some food critic and cook style checks on our code. How do we build everything together? So in our lab, in our offices, we have a build server. We use a Jenkins for that. That triggers a Linux build server, and the Linux build server is Cobbler. Maybe some of you know that. And the Cobbler installs the basic image, the operating system on the platform, plus the Chef client. So the chef client then takes over and sets everything up on the platform as needed. For our virtual machines, we use Packer to build them, and the Packer run also includes the chef client run. So after everything is built, we put it together in our lab, and we are able to test what we did there. The testing, we have a lot of automated tests. They are mostly written as server spec tests, but we also have some manual testing, especially for the hard drive changes. How do we guarantee that the trains don't get the latest cookbook version we release? We work with chef environments. So we pin the cookbook version in the environments. So a train that is on the release 5 only receives the cookbooks that are in this release 5 environment. And as soon as a new major release is deployed to the trains, these trains get the cookbooks that are in the release 6 environment. Our chef servers, so we have 4 different stages. As probably most of you, we have development, test, acceptance, and production stage. And we have 4 different chef servers for that, so each stage has its own chef server. And what are we actually staging? We are only staging the cookbook pinning in the environment file, because that sets the release versions. And per environment, we have, of course, environment-specific attributes and databases with different, like URLs and so on. So in the end, our platform is fully manageable over the air. We achieved that. We can release new features really fast. We can apply security patches really fast. And all trains have a 4G connectivity because they are connected to the new internet gateway. Other manufacturers provide their virtual machines, for example, video streaming. And all of these things are stored locally, so there's also no interruption whenever a train goes through a tunnel, which can happen quite often, of course. And one of the best parts, of course, is we don't need the approval of the railway authorities, because we are not directly connected to the train systems. And so we are really flexible, and yeah, what the name of our project says, Flexible Vehicle IT, we finally made it. And there are a lot of applications for customers and also for the train staff on the way. And that's it for my talk. And maybe when some of you are in Germany and take the train, just remember a part of this community is on board, and yeah, I hope you have a great experience. Thank you.